Hello, my name is Jake Noltensmeyer. I'm a physics major at Texas Tech University, and my thesis is entitled Signal Analysis for the Production of Non-Thermal Dark Matter at the Large Hadron Collider. So the purpose of this thesis is to study the feasibility of using the CMS detector at the Large Hadron Collider to search for dark matter. To give a bit of background, in physics we have what we call the Standard Model, which is a theory that describes all the fundamental particles and their interactions. Dark matter is a theoretical particle, or perhaps a family of particles, outside of our current understanding of the Standard Model. The most significant trait of dark matter is it's limited to no interactions with any of the known fundamental forces, with the exception of gravity. This has led to the term weakly interacting massive particles, or WIMPs, to describe the most probable dark matter candidates. This creates an interesting problem, because while we have known dark matter exists for decades now, due to its gravitational effect on galaxies and the light that passes through dark matter clusters, we've never been able to register a successful detection of a dark matter particle. This is where the Large Hadron Collider at CERN comes in. The LHC accelerates protons to nearly the speed of light and collides them in one of the 4 detectors situated along the beam path. The energy released in these collisions creates new particles which can then be studied by the detector's various components. It's possible dark matter particles could be created in these collisions. Using conservation of momentum, we know that the momentum of the 2 initial photons must be equal to the sum total of the momentum for all particles after the collision. Although dark matter will escape the detector without being registered, this leaves an imbalance when comparing the initial and final momentum, which can tell us that a dark matter particle may have been produced. This is what's known as an indirect detection. We aren't detecting the particle itself, but we're detecting the missing momentum that it escapes with. Unfortunately, there is a problem with this method. Certain standard model particles, such as neutrinos, are also able to slip through the detector and leave missing momentum. Thus, our study looks at simulated missing momentum curves of known background sources and compares them to the missing momentum curve of dark matter in order to ensure that the CMS detector is able to discern the latter over the former. Something to note is that while missing momentum studies have been conducted before, the models that we study in this thesis are unique in their production of a single dark matter particle as opposed to most previous models where dark matter was produced in pairs. In these scenarios, the dark matter particles travel in opposite directions, and that causes the missing momentum to cancel out, which makes the detection of these dark matter particles difficult. For me, the best part about this thesis was the amount I was able to learn about both fundamental particles interactions and how those interactions are analyzed in a particle collider such as the LHC. I'd like to thank my thesis director, Dr. Shuichi Kunori, for his support and guidance over the course of this year, as well as Dr. Nural Akchurin for his recommendations for revising and improving my thesis. Thank you.